Have you ever played with an ant farm? I'll bet you weren't expecting to see this in statistics class today. But as it turns out, an ant farm is one of the best visuals that I can think of for a set of data on a graph. And it's especially important for today's topic, which is called measures of position. This is discussed in section 3.3 of the book. It's our final lesson for week 2. We're going to go back to this pile of sand visual in just a little bit to talk about measures of position. The two main measures of position of interest in our class are the z-score and the percentile. Now, first of all, how is a measure of position different from a measure of center or spread, like we've discussed? Measures of center, remember, those are the M words, mean, median, mid-range, mode. And the measures of spread are things like standard deviations and range. Now, those numbers are summaries that describe an entire set of data. A measure of position, on the other hand, is something that's going to describe only one number in that list of data. So if you have a list of thousands of numbers, every single one of those numbers has its own z-score and its own percentile. So what are these numbers for? The z-score is going to be a one-dimensional measurement from left to right, telling us how large that data point is. In other words, where that data point falls on the. By contrast, the percentile is a two-dimensional measurement, area, and that's going to tell us how common the data point is. In other words, where the data point falls on the pile of data. So remember this distinction. We've been discussing this duality of data for quite a while now. When we've set up a frequency distribution, what we're doing is we're basically listing how large the numbers are in our left column, and then how common they are on the right-hand column. When we graph that, the largeness of numbers becomes left-right, and the commonality, frequency, becomes vertical. So these are two numbers, again, that relate to that issue. So let's see how we can visualize these concepts. So here again is our pile of sand. Each grain of sand is analogous to one number in the data set. But when we pile many of these numbers on top of each other, they start to pile up, especially where those numbers are most common. And the most common ones pile up the highest. So when we see this on a statistical graph, of course, we're normally going to see an x-axis that looks basically like that. And we would normally go up to the top of this mound and trace over top of it in a manner that looks something like this. Now that's of course much easier to draw than a whole pile of sand. But when we trace over the top of the data, it can be a little bit misleading sometimes because it kind of just makes us look up here at this curve floating up in the air. But we must always remember that it's not just floating up there. It's only the top of a big pile of numbers. Okay, so to illustrate today's concepts, let's just pick one individual grain of sand. Let's pick this guy right here. There's that little black dot is one grain of sand or one number in the list, which will be of interest to us. So the first question we can ask is, how large is this data point? And we know that that's measured on the x-axis. So we might think about kind of just dropping straight down from that point like this until we hit the x-axis. And that point of intersection here would tell us how large it is. Now we've already seen this concept. We're going to look at a slight variation on that theme today to describe how a z-score is also related to the size of a data point. Now, the percentile is going to be a two-dimensional area to the left of this point. So let's go ahead and continue this this value and create basically a cutoff. And so that basically cuts off the data into the numbers that are smaller than this one versus the numbers that are larger than this one. And if we think about all the numbers that are smaller than this one to the left, let's go ahead and shade those red with a very thick marker pen. Okay, if you think about the area of all the data to the left of our favorite data point, you get this two-dimensional area or percentage. Remember that areas measure percents or proportions. And that's what we would call the percentile of that one data point. So the fundamental question in statistics class basically comes down to what's the relationship between how large a number is and how common that number is. So the z-score and the percentile are really fundamental measurements of those two properties. Now, let me take you back a little bit to review something, because this z-score, you might remember, is a concept that we've already foreshadowed. Remember when we drew this distribution of the prices of electric cars, electric vehicles? And when we listed the prices from left to right, we discussed how the one in the middle has a z-score of 0, and the number that's one standard deviation above the mean has a z-score of 1. A score that's one standard deviation below the mean has a z-score of -1, and so forth. So the z-score answers that fundamental question not only by saying how large is this number, but more specifically by saying how many standard deviations is this number above the mean. How far above the mean is this number if you measure it in units of standard deviations? So we've already basically seen what z-score is, but we need to get into the nitty-gritty now of actually calculating it, because it's usually not as simple as 1 or -2. So there is a little formula for it. I think it's a pretty intuitive formula. And that formula involves subtracting and then dividing. So I'm trying to zoom in on it here. Okay, so the z-score is x minus mu over sigma. And to remind ourselves what these symbols mean, the standard deviation is sigma, the mean is mu, the grain of sand that we're interested in is the value itself, which we call x. So how many standard deviations is this value above the mean? And if we're using these symbols for each of those concepts, if we translate that question into a formula, it looks like this. Why does this formula make sense? Because the z-score, again, answers how far above the mean is this value. And we do that by subtracting x minus mu. But then we continue the question by saying, when it's measured in units of the standard deviation. And that's why we divide that difference by the standard deviation. All right, so that gives us a z-score. That z-score will be 0 if the number that we're looking at is right at the mean. It's going to be negative for numbers below that mean and positive for numbers above that mean. So that's what the sign tells us, whether it's a positive or negative z-score. And then if we ignore the sign and look at the number part of it, the absolute value, the takeaway here is that the larger, the rarer. And we usually use the number, a number of about 2, a z-score of about 2, to represent the cutoff between typical and unusual values. Let's illustrate this with an example. Okay. Each data point in a set represents a student's SAT math test score. The scores have a mean of 500 and a standard deviation of 100. And that's basically true, by the way. That's how z-scores are, or how SAT exams are scaled. Penelope's score was 360. So Penelope, in this case, is the grain of sand that we're interested in. What is her z-score? And how do we interpret it? Okay, so let's go back to that formula. Okay, so here's the basic z-score formula again, x minus mu over sigma. And we must always remember what each individual symbol means. So this means Penelope's score minus the average score divided by the standard deviation. So in this example, it's given to us that Penelope's score was 360. as compared to the mean, which is 500, with a standard deviation of 100. So we can just plug those numbers right in there. And I believe this is going to give us a negative 1.4. 360 minus 500 is negative 140. And if you divide that by 100, you get a z-score of negative 1.4. So let's interpret. How is Penelope doing compared to the rest of her class? Well, for starters, her z-score is negative. What does that tell us again? If Penelope's score is negative, it means that Penelope is below the average. However, if we look at the absolute value of her score, 1.4, it's not as big as 2. If her z-score had been below negative 2, that would have told us that not only is her score low, unusually low. Like, we need to be concerned about Penelope. But in this case, 1.4, it's not that bad. So we might say that in the grand scheme of things, Penelope's score is actually pretty typical. It's below average, but it's in the typical range. Now, it's important to be able to answer that question in reverse. So let's suppose, for example, that there's a selective college that only takes students that have a z-score of 2.5 or better. So we would be interested in flipping this question around and saying, if I want to target a z-score of 2.5, then how high should my SAT score be? So we can basically do that with the same formula, but we're going to need to do algebra. Either, well, you have an option. You have a choice. You can either do the algebra on this formula. You can either do algebra before you plug in, or you can do algebra after you plug in. Or if you don't like to do algebra, then you have to memorize a new version of the formula. But let's just see how that works. So in this case, and I think it helps to have the formula spelled for us with letters first. All right, so if we want our z-score to be 2.5, we can plug that in here. What score are we looking for? That means that x is the unknown, so it will remain a letter this time. But we're still assuming the same parameters, that the mean is 500 and the standard deviation is 100. Okay, so what I mean by doing algebra is after we write this formula, the x that we're looking for is not isolated. It's buried with other numbers. So we'll just have to take a couple of algebraic steps to isolate it. For example, we could multiply each side of this equation by 100. And that would give you, sorry, not 2,500, 250 equals x minus 500. And then we can add 500 to each side and find that our desired SAT score, x, is 750. I believe that in this chapter, you won't be tested on this step, but that will be coming up. It'll be important later in the course. So I'm just kind of previewing it now. But for now, for the homework 2 and the quiz 1, you will be tested on just calculating a z-score like that. Okay, so let's leave this video clip here. We've covered the overview and the z, and we'll be able to pick up percentiles in the next video segment.